Hello, I'm Chris, and in this session we're going to talk about peripheral communications. When we talk about peripheral communications, we're talking about how the Meadow microcontroller or computer talks to peripherals. We've got several different communication paths. Some of the common ones are asynchronous serial or a UART, so we're talking traditional serial ports, RS-232 or RS-485. We've got a group called Synchronous serial ports. Those include I2C or SPI. We also have the Controller Area Network or CAN bus, which is common in automotive and manufacturing. That is coming post V1 release. We also have a couple of more esoteric things that aren't used terribly often anymore. A common one is one-wire communication for some peripherals. We've got this in our backlog. There's no specific time on it because we haven't really had anybody specifically asking for it. Then we have other ones like the WS2812 LED light strips. This is again a backlog work item that we have. For now, if you really need one, you can use a separate controller. We do have a peripheral called the Serial Wombat, which is a separate microcontroller that can drive these. I'll talk a little bit more about both of these later and why it's challenging to do these. But first, let's talk about the synchronous versus asynchronous serial. The primary difference between these is how the bit timing happens. So in an asynchronous, we have a crystal that handles the timing versus an synchronous, which has an external clock and a clock line. So really when you're looking at it, if it's got a clock line, then it's a synchronous serial port. For asynchronous serial, again, this is like our common serial port. We have a fixed bit time. This bit time is based on a crystal and it has to be set on both ends. So both the transmitter and the receiver are sending and receiving at the exact same time. A good example here is at 115.2 bits per second, it's 8.68 microseconds between bits. So we've got a clock that runs and the receiver reads every 8.68 microseconds, and the state of the data line is that data value. So it has to be consistent and it has to be the same on both sides. The upside is it only requires one line for data transmission. Typically there's a send and a receive, so you've got two lines, but this is how an asynchronous works. Synchronous serial, however, works a little bit differently. It's got a max rate, so you might see something like 400 megahertz, or 400 kilohertz rather. That speed is really the maximum speed that you can run, and it is dictated by how fast the peripheral can actually service the data. You can run much, much slower than that speed because what happens is you've got a clock line, and that clock pulses, and when it goes high, whatever the data line is set at, that is the data. So it doesn't matter really how fast or slow that clock goes if it can be serviced on both ends, as long as the data line is set when the clock goes up. You'll see that data. You can see in this example here, the data line goes up before the clock and comes down after. This is pretty typical because if you're writing this in software, you set the data line, then pulse the clock, then set the data line to the next data value. Specifically, if we look at the I2C or I2C bus, this is a multi-peripheral bus. So you can put multiple peripherals on the bus with just a data and a clock line. The way that it communicates with a specified peripheral is you've got an address. So the address and the direction is sent first and then followed by the data. So you've got two lines, clock and data, and the clock is driven by whoever is sending the data. So if you're communicating from the Meadow to a peripheral, the Meadow drives the clock for the request, then it releases both lines and the peripheral drives the clock to send data back in a response. Another synchronous serial is SPI, or SPI bus. It works a bit differently. Again, this is a multi-peripheral bus, so you can have several devices on the bus, and typically these are selected by what's called a chip select, so you have a separate GPIO that is active low. You pull it low for the peripheral you want to talk to. So if you've got 5 peripherals, you have to have 5 extra GPIO that you can run to the chip selects on them. If you only have one, oftentimes it will just be tied low, so you don't need that output bit to drive it. It's just always enabled. The other difference here is you've got 3 communication lines outside of that chip select. You've got the clock, and then you've got 2 lines for data, one for out, one for in. When I say out and in, we're talking from the controller perspective, so from the F7. Out would be going to the peripheral, in is coming back from the peripheral. One of the important distinctions here is this clock is driven only by the controller. The peripheral has no control over this. What that means is the controller, when it sends data, if it's expecting a response, it must know how much data is going to come back because it has to drive the clock enough times to get all of that data back. Another thing that is a little bit confusing to people is that because of this behavior, data is always going in both directions. When you're sending data, you're also receiving data. Now, the data may be something that's completely irrelevant, and in this case, you can see we've got this data out where we're sending data. When we drive this clock to push that data out on the bus, data comes back into an input buffer. Typically, it will be all zeros if the peripheral isn't responding. And then when we want to read back, we have to continue running the clock, which means data is going to go out, and the peripheral will ignore these zeros. Now, this is a pretty common way to see it, but some devices, some esoteric ones, will actually allow you to multiplex and do send and receive at the same time. It's not common, but it does happen, and there's nothing that this bus has that would prevent that from occurring. Now, again, we've talked about the others. We've got the CAN bus, which we're working on, and these other 2, the WS2812 and OneWire, those are really an asynchronous serial as well. So they've got specific bit timings, and the bit times are very small. Now, that very small bit time is really difficult to achieve in managed code, especially with garbage collection where you may have pauses in it. So it's difficult to reliably have bit times that will drive these peripherals. We are looking to either push the driver down into the real-time operating system or potentially a separate controller. So that's how those work. If you've got questions on something like one of these devices that you need in your solution, talk to us and we can come up with some solutions that should help provide a resolution for you. Another just side note is protocols. There are a lot of protocols that sit on top of these communication buses. Common ones might be things like Modbus, which is used in industrial. It sits on an RS-485. We actually have libraries for both client and server for this. There are also the J1708, which is used in transportation and telematics. It runs on 485. That has largely been superseded by J1939, which is, again, communication for vehicles, but this time on the CAN bus, or controller area network. The CAN bus is real common in a vehicle. If you've got a check engine light and you plug in a reader, it's reading the CAN bus to find out what is going on the vehicle. So how does this affect our peripheral drivers? We've got a whole bunch of drivers in Meadow Foundation, but you may want to create your own for some peripheral we do not yet support. So a driver will use this bus, and the idea is that the driver handles reading and writing data to and from the bus and abstracts that reading and writing into more friendly APIs that a application can use in order to get data from the peripheral or send commands to the peripheral. So for example, this is a gyro. What we would do is you create the I2C bus, and then we pass that into the peripheral driver, and then from that point on, all we do is we tell the peripheral commands, such as wake in this case. That wake then will send a command over to the gyro. It actually sends the address and a write bit, and then it will send the data to it, and then if the data or if the peripheral has a response, it will send that back. And there you go. There's a rundown of the communication buses in the Meadow stack. If you have any questions, by all means, ask them in whatever streaming system you're using. We'll try to get to you. And otherwise, thanks and have a good conference.